Okay, so we are going to talk about the transformers because this is the very hot topic, and you guys have learned about the CNN, the convolutional neural network, which started this revolution, and lately transformer had taken over, and most of these things you are hearing about GPT 1, 2, 3, and ChatGPT, and GPT-4, and all those. Stable diffusion and all this image, text image modeling is essentially using the transformer. So transformer is this. There's encoder and there's decoder, and it essentially, the important part of transformer is called self-attention. So this is the multi-head self-attention, and in that the concepts are query, key, and value. We'll go through that, and then other is called position encoding, which is here, and then of course there's an encoder and there's a decoder. So transformer is used for modeling long dependency between input sequence elements, so it will model a sequence, and the important difference between transformer and LSTM or recurrent neural network is that we can do parallel process of sequence. We can look at all the tokens, elements of sequence in parallel. It's not sequential. So it doesn't require any inductive bias for its design, so that's why it can work for multiple modalities. Like it works for images, for video, text, and speech, and uses similar processing blocks. And typically, transformer are used pre-trained using pre-test tasks on large scale data set, and these are typically unlabeled, and self-supervised learning methods are used for that. And good thing is that, you know, this demonstrates excellent stability, very large networks and huge data sets. It really works very well. So recently in computer vision, transformer will be used in recognition tasks like image classification, object detection, action recognition, and segmentation, generative modeling, multimodal tasks, visual question answering, visual reasoning, visual grounding, video processing, activity recognition, video forecasting, and low-level vision like image super resolution, image enhancement, colorization, and so on. And also 3D analysis like point cloud analysis, classification, segmentation like LiDAR data, and so on. Okay, so it is started in the natural language processing, NLP, and of course NLP transformer has been used heavily. BERT is a very famous model, which is bidirectional encoder representation from transformers. Then GPT, as we have been discussing, generative pre-trained transformer version 1.3, and ChatGPT, and maybe V4. Roberta, robustly optimized BERT pre-training. T5, which is from Google, text-to-text transformer. Now we'll talk a little bit about BERT because it's very popular and works pretty well. So the original transformer model, you know, could only attend to the context on the left of a given word. So if you have a sentence, so it will look at the whatever it has seen before, it will attend to. But BERT actually changed that you can look at the right context and left context in the sentence, and it makes improvement in the feature representation. So BERT is trained on 2 pretest tasks in self-supervised manner. Self-supervised training means that you don't have to have labels, okay? So one is called mass language model. So the idea is that you have, say, a sentence, and in that you mask out 15% of the words and have the network predict the mask words, okay? So of course, it's a self-supervised learning because you will know the original sentence, you mask out and you know what should be, so you can have the ground truth and then try to minimize the error and learn the representation. So in predicting the mask words, the model learns a bidirectional context. That learn this word, what were the words before and what were the words after. So that's why bidirectional. The other task is next sentence prediction. So it will given two sentences and model predict whether this pair is valid or not. So the original, they will look at document, look at the adjacent sentences, and it will predict is correct pair or not, and that's the way it will learn the encoding. So in this thing, what they do, the 50% of the time they have the right pairing, and other 50% is random sentence. So transformer, as I showed you earlier, it consists of encoder and decoder blocks. And sometimes you just use only encoders, sometimes you use both encoder and decoder. So you want to keep in mind. So main components of each block, whether it's an encoder or decoder, is self-attention. So self-attention is the main, gist of the transformer. And we are going to spend detailed time to really make it very clear to you guys. So, and the next component is called layer normalization, which is pretty easy. I mean, it's kind of similar to batch normalization, which you have been using. And then feed-forward network, which is also you are familiar with. So we start with encoder. So this is the input. So input will be some initial embedding. And then we'll add the position encoding. Position encoding is represented by this symbol. And then that will go, we will compute key, value, and query. So these are the words you will keep hearing on a transformer. So that will go to the self-attention. And then we will get out, and then we'll do add normalize. And then we will have the fully connected layer, then add normalize, and we can repeat this n time. These are the n layers. Okay, so this is the key. So then we have a decoder. So decoder is same structure as I said, material attention, add norm, material attention, add norm, fully connected, and so on. So the thing here is that we will get the encoded input, which will go to the decoder, and also it will have position encoding, and this will come from output of the decoder, right shifting. So that's the way the encoder and decoder works. And again, we can have n blocks like that, n layers. So a little bit more detail, what's material attention? So it will consist of query, key, and value. We'll talk about this. This will be a scale product attention. Then this can have multiple heads. We'll do many times. And so we'll concatenate these outputs, and then that will be our thing. So this is the self-attention block, query, key, value, and we will multiply, scale, and so on. We'll talk about that. And so we'll have, multiple version copies of this here. That's why multi-head attention. Okay, so now the concept of self-attention. So let's say we have a sentence, how are you? So these are the 4 tokens or 4 words. And so we will do initial embedding of each of word. You can use a word to vec or whatever. So each word will be mapped to a feature vector. Vector will be numbers. So that's why it's called word to vector. So we will get these, and let's say this will be the first word. And this is just example, the 4-dimensional vector for them. Hi, This is how 4-dimensional vector and so on. So the intuition about self-attention is that we will find out a dot product, the similarity between given word with all other words. So this is a dot product of the first word, the second one, just say here, 0.21. And we'll do that for the first with third, first with fourth, and this was for first word, then we'll do second with 1, second with 2, second with 3, and so on. So this matrix W star is kind of capturing that how similar this word high is. It's capturing the context from the other words. So when we did the word to wake, we were just looking at individually each word. So there was no context. Now self-attention is kind of capturing the context, and that's very important because in the language, in the images and all this, there's a context, and that's what we want to capture. So the starting point is the dot product cosine similarity, and we are going to do that. So now what we are going to happen, so we'll do normalization, convert to softmax so that they sum into 1 and so on. But given this W star matrix, so we are going to take the original embedding, which was this one, as I showed you earlier. We will transpose that and multiply with W matrix. So each of this embedding will be multiplied with this matrix, which will have some context information from other words. And this is basically the attention, right? So saying, well, how similar the first word is the second word, or third word, and fourth word. So that's a beginning of kind of taking the attention from the other words to the given word. Okay, so that's the basic idea. Now, of course, here there's no learning. Everything was fixed. We just the word to wake, and then we find the cosine similarity, and we then took this W matrix and multiplied with this, and that's what we got. So we got a little bit, attention from the other words, but there's no learning because, as you know, in deep learning, the whole thing is that we have to choose learning. We have to learn a lot of things, and then things will work. So now we are going to do actual learning. Okay. So here's an example. So please listen to this carefully. This is a very important concept. And once you understand, then you will understand basically the whole transformer idea. So let's say we have a very small image, which is 3 by 3. And it is, has 3 channels. Okay. And so we have basically 9 pixels here. Okay. So each pixel we can consider as a token. So we'll use this language, this terminology a lot in transformer. So tokens, so words are tokens, and we will talk about pages and all this thing. So here we have 9 tokens, and each token is 3-dimensional vector. Okay. So we want to take, and this can be image, or this can be feature maps, different layers and so on. So we want to take this X maps, image feature map, and we want to apply self-attention to that to get this one, so that this is a better features compared to this one, so that this has more context of other tokens here. And right now, each token is individually encoded. So that's the idea. So what we are going to do, we'll take this feature map, this 3 channels of 3 by 3, and apply 1 by 1 convolution. We will call this key, and we'll get another 3 channels of 3 by 3. Similarly, we'll have another 1 by 1 convolution query. We'll get these 3 channels, and then we'll have value, also 3 channels. Okay, so it's very simple. So this 1 by 1 convolution. Now what we're going to do, we'll do the transpose of this and multiply key with query, and that will give us 9 by 9 matrix. And this is basically attention map, and it's very important. You need to understand that. So as I showed you earlier, that we had this 4 by 4 matrix. So this is basically, now since we have 9, there we have 4 words, here we have 9 tokens, 9 pixels. So this is basically telling you that the first token, how much attention we have from the first one, second one, third one, ninth. Similarly, second row says second token, how much attention it has from the other tokens and so on. So we'll take the attention map, then multiply with the value, and then on the top of it, we'll do 1 by 1 convolution, another one. And then we'll get this 3 channels of this 9 pixel. So that's basically is the self attention. So as you see, that in a way it's similar to what we discussed, the toy example, but here the main difference is that we are learning this 1 by 1 convolution, this one, and this one. So that's better than just doing the dot product as we discussed earlier. Okay, so let's go in a little bit more detail. So now we have this n entities, in this case 9, but it can be any number, x1, x2, xn. And and each of the entity is the n, d-dimensional vector, in this case 3, but it can be any dimension. So n here is 9 and d is 3. So given that, then as we talk about, that we will have this WQ matrix, WK, and WV, which will kind of do 1 by 1 convolution. So this matrix will be D times DQ, D rows and DQ columns. Similarly, this is D rows and DK columns. And then this is D rows and DV columns. And we are going to assume that DQ and DK are same. Okay. So now, first we want to project the X to Q, K, and V, as I explained here. So we are going to take the X, multiply by WQ, which is this one, get the Q. We'll take the X, multiply with WK, we'll get K. And similarly, we'll take X, multiply with WV, get V. So then the output will be Z. And so this is what's shown. Q, K transpose, multiply. We'll divide by under root of DQ, which is a dimension of the query. And then softmax to normalize everything. Then multiply with V, we'll get Z. So this is X, this is basically Z here. So the same thing here, what we are talking about in terms of matrices. Okay. So that's the initial thing. Now let's go more detail. So again, we have n tokens and we have X. So right now we are going to introduce actual numbers. So as I say, we have n is 9 and d is 3, as shown here. So then we have these WQ, WK, and so on, and we can put these. So our WQ will be 3 by 3 matrix, okay? Because D is 3, and we are going to, fix the DQ as 3. And same way, WK is 3 by 3, and WV is also 3 by 3, okay? So we'll multiply these. When you multiply, so X is 9 by 3, as you see here, and WQ is 3 by 3. So therefore, we will get 9 by 3. That will be Q matrix. Okay, that's very simple. So same way, we'll get K will be 9 by 3 and V will be 9 by 3. It's exactly the same. So now we have Q and we have K. Now we'll do the K transpose. So K transpose will become 3 by 9. So now look at this. So this one is Q is 9 by 3, and this K transpose is 3 by 9, so that will become this will become 9 by 9. Okay, and then V we already know is 9 by 3. So therefore, at the end, we will get 9 by 3 after the softmax. So that is this one. So this, in terms of matrices, that's actually the coding. That's what you will do. So now this started with this paper, very influential paper, 2017. The title was Attention is All You Need. Published in Europe 2017, less than 5 years, maybe 5 years ago. 62,000 citation, for this paper. So that's really amazing. And now there's a lot of blogs, a lot of resources, and I'm actually using that to make it very clear. So this is a very nice blog here from Harvard. There's another blog here, and I'm using slides from this one, and also a nice presentation from the University of Waterloo. Okay, so let's go more detail. So we have a transformer. As we say, we have encoder, many blocks. So here we are showing the 6 blocks, and we have decoder, also many blocks, 6 blocks. So we're going to look at example. The transformer can be used for machine translation. Okay, so we have this French, we want to get the English. So we have encoder, the input goes encoder, and the output comes from decoder. So encoder block, each block is same structure, but different parameters, like layers in your CNN. So main thing, as I said, is a self-attention, which I just explained, and the feed-forward neural network. So let's go in a little more detail. So let's say we're going to look at actually a very simple example, 2 words from this very nice lecture. Thinking machines. Okay. So we want to translate that. So we will take this word and do the encoding, initial encoding, embedding. So this one says 4-dimension machine. So then we are going to apply the self-attention. From X, we will get Z. X1, Z1, X2, Z2. So then it will go to the feed-forward neural network. And from there, we'll get R1. And from here, we'll get R2. So that's the feed-forward neural network. It will be independent for each word. So therefore, we can parallelize. We can do this quickly. Okay, we don't have to wait for this sequence like LSTM will wait. So we can do this one directly. Okay, so here's more, detail. So we have thinking machine. We do embedding X1, X2. So then, as we said, we are going to do self-attention first. So we will generate query, key and value for this word, and query key and value for this word. It's Q1, K1, Q1, and this is Q2, K2, V2. And the way we're going to do that by multiplying this WQ, WK, WV, as I explained earlier, matrices. Okay, so here we have 4 rows because it's a 4-dimension. Other one we have 3, but doesn't matter. And so first we create 3 vectors, which are the query, key, and value, by multiplying input embedding, which is this one with these matrices, 3 matrices. And this is the way we explain, and we'll get those. Okay, so then we are going to do next step, and we'll take an example here. Let's say when we multiply this next step, you saw the transpose. So we multiply query with key for the first word, and let's say we get number 112. And then for this one, we get 96. These are just upward numbers, but just demonstrate what you're going to do. So we want to calculate the score to determine how much focus to place on other parts of the input. As we say, we want to capture the context, and I give you example in the beginning. So we went through the process, and now we got this one. So then we are going to divide by the dimension decay. So it's 8, so 112 divided by 8 is 14, 96 divided by 12 is 8 is 12. Then we will do softmax so that we sum to 1. So it's 0.88, 0.12. So now, once we get after softmax, as you remember, that we multiply by VIN. So that's why 0.8 V1, 0.12 V2. Now this is Z1, starting from X1, Z1, it captures the context of the second word also. So that's the idea. And we're going to do the same thing for the second word. Okay, so this is a formula. As we say, we have a query multiplied by K transpose, divide by the under root of dk, softmax, multiplied by value, we get a Z, and the Z1, Z2. So it's very nice. So then now this was just one self-attention head. We will have multiple heads. The repeat process, and as you have done in layers in CNN. So let's say we have 8 heads, Z0 to Z7. So each of the head will get this 2 vectors. From starting from X, we'll get 2 vectors from first head, 0th head, 1 head, and so on. And so the reason, as you have learned from CNN, that we want to have many filters, many layers, so that we want to learn a lot of things, so it expand the different abilities. So it gives attention layer multiple representation of subspaces, and so then at the end of this, we will have for those 2 words, thinking machines, we will have one from the 0th head, this from first head, and so on, like that. Then we are going to combine those, multiply with this matrix WO to merge that, and we get at the end will be just 2 vectors. This one for the thinking, this for machine. We have done all those things. Capture the context. Okay. So then in summary, so we have our sentence, which is thinking machine. We embed each vector like this X. We split in 8 heads. We multiply with this R matrices, these 3 matrices for each head. We calculate these Q, K, and V matrices, and we get Z0, and like that we will get for the other heads Z1, Z up to Z7, then multiply with this W matrix and we get Z. So that's a summary. Okay, so this shows you that we have these 8 heads here, and this is the sentence. These are tokens, and this is saying that it word, how much attention these different words are paying, and this is just, we are showing only 2 heads, the orange and green one. So then this is showing all the heads. So that's what we are doing here. Okay, so now this representation, as we did parallel, it is there's no order, so which means that this is transformers permutation oriented, permutation invariant. You take a sentence, you permute, still will be similar representation because it doesn't have any order. So we want to put the order. So that order will be that we will add a vector to each input embedding, and that's called position embedding. Okay, so that is important, that how do you come up with those position embedding, and there's a lot of interest in that. It will learn, pattern, this position helps model to determine the position of each word and also the distance between different words. Okay, so which means, like this is your sentence, and in French we get the embedding 3, then we are going to add this vector position encoding, the same dimension as this one for each of this. So from here we get now, after addition, like this. So then it'll go to encoder 0, 1, and so on. So now position encoding, we are going to do one way is a fixed encoding, which will be sine and cosine, alternate sine, cosine, sine, cosine, and so on. And so this is the way we're going to do that. We will run through this loop from 2k, then 2k plus 1, and these are the frequency wk, which will depend on the dimension k. I'll give you concrete example. And so that's it. So now if you look at this position encoding, where we have 128 dimensional size of a vector, and we have 50 different tokens. So each of these is different, and that's what we want to do. That's where we can distinguish different tokens. So in this cosine sine pattern, they found out it's to be pretty good. So let's look at specific example of this I am a robot, how we do position encoding for that. Okay, so we have a sequence, I'm a robot, we have 4 tokens or 4 words. This is the index of token, which is k, 0, 1, 2, 3. And this is a formula I showed you. This is the way we are going to do sine and cosine. And so let's look at first one. So we will have, I goes 0. So we'll have for that one sine cosine, then that I is equal to 1, then sine cosine. So since we are going to limit to 4, so we'll have just 2 values of I. And we'll pick cell n is equal to 100. Okay, so therefore, when the I is 0 and k is 0, if k is 0, this whole thing is 0. Okay, so sine of 0, that's what we have, and cosine of 0. Okay, so which is 1 and it's 0. Then in this one, even though I is 1, but k is 0, so again this will be sine of 0 and cosine of 0. So that's very easy. So this is a position encoding of this first token 0, 1, 0, 1. Now let's look at the position encoding of aim. So here now k is 1. Okay, so therefore k is 1 here. So then we have I is 0. So therefore this whole thing is 0. So therefore this will become 1. So this is 1 upon 1, sine of 1 upon 1. Sine of 1 is 0.84, cosine of 1 is 0.54. So that's easy. Now here we will have I is equal to 1. So k is equal to 1, I is equal to 1, so it becomes 2, d is 100. Okay, so under d is 4, sorry. So d is 4, so 2 upon 4 is 1 upon 2, and n is 100, so under root of 100 is 10. So that's why we have 10 here. So sine of 1 upon 10 is 0.1, cosine of 1 upon 10 is 1. Okay, so keep going like this. So here we will have k is equal to 2, and you can figure it out yourself, and like that. And that's our position coding. So that's the way it's going to work. Okay, so now position coding. So this was the fixed position coding, but position coding can also be learned. So we'll just initialize randomly, And those will be a parameters as we learn the one-by-one convolution and all those things. So that also is what, and actually learning a position encoding is better. Okay, and just learn like other parameters. So already went through that. Okay, so now we are getting close to finishing this. So we have thinking, machine, position encoding, X1, self-attention, Z1, Z2. Then we're going to talk about the layer normalization. Okay, so now layer normalization idea was in my intent. So we want, because there are different layers, so we want to make sure that these features are normalized for the next layer, that each layer treats equally. So you guys are familiar with what's called batch normalization, right? So we have, say, 3 batches. Then we compute, for each of element, compute mean and standard deviation, we subtract mean, divide by standard deviation. That's called batch normalization. Now, layer normalization, we do other way. We compute the mean of this, each of this, and then standard deviation each, and subtract mean and divide by standard deviation. That's called layer normalization. So then we are kind of done, because we have self-attention. And now what we are going to do is we will have this skip connection. After self-attention, we are going to take this and add it with after self-attention, skip connection, as you heard in the ResNet and so on. So that's the idea again here. So that's it. So here we have encoder, here we have a decoder. And now if we use both, then output of encoder is going to go to decoder, and this will become the key and value we'll get from encoder, and the query will become from decoder. So this is kind of cross attention. Self-attention, key, value, and query were from same thing. But cross attention, there are 2 things. These are coming from encoder, and this is coming from the decoder. And that's the way it's going to work. Then same we're going to repeat that. Okay, so that's the basic of the transformer, and this is in context of the NLP, the words and tokens and so on. So that was 2017, and there was a lot of time this transformer idea didn't pick up in computer vision. And this was in a way first paper which used transformer and vision transformer, ViT, and then title was image word 16 by 16 words. So because it came from NLP, so therefore they have words, sentences, and now image is different. So we want to take 16 by 16 page and consider as a word. And this was published in 2020. Now it already have 10,000 citations. Okay. So now you can do self-attention, at the pixel level. You can consider each pixel as a token, but there'll be a lot of computation, so that's not possible. So that was a problem. So what they did, they divided an image into 16 by 16 pages, and each page become word or token. And but also the transformer needs large data set to train, and these other transformer, BERT and so on, they were used by Wikipedia and all these big text, because there's a lot of data in text. So that's why these guys, they actually got this their own data set called JFT 300 million images trained on that. and that was the ViT. And they got pretty good results on ImageNet 88.5, on ImageNet Real, and all those things. C4, good results. So how does it work? So what you do is you have an image, you divide image into 16 by 16 tokens. This is each token, and take each and flatten this, and then do some linear projection to map this in a vector. And so these would be tokens 0, 1, 2, all these tokens. And this is a position encoding, then the transformer. Then the same thing as we talk about self-attention, value cube, query, and normalization, and all kinds of things. So this is just encoder now. So you want to get good representation of image, and then you add the MLP head, and you can do the ImageNet classification. 1,000 classes. Okay, so this is again your transformer encoder. Patches, normalization, material attention, skip connection, and all those things, and AL copies of that. So we will divide image in 16 by 16 patches. Let's say your typical image is 224 by 224, and now it looks like this. So it'll be 14 by 14 pages. 14 multiplied by 14. Each row is 14 pages, and it'll be total 196 pages or tokens, and each page is 16 by 16, and then 3 channels. So then it will look like that. So this is one token. We have 768 dimension vector for that, because 16 by 16 is 256, multiplied by 3 is 768. So this is embedding for each of the page, and 196 of those. Okay, and so typically what we do, we add the additional token, which is called CLS token for classification. So that will capture everything in the image, and that's what we can use for MLP to classify. So then we have 197 tokens. So complete ViT is like this. Take the 224 by 224 image, divide into 16 by 16 pages, 196 pages, project, get the 768 dimensional feature vector, embedding, add the positional embedding there, and then go to the encoder, and then comes out the prediction of ImageNet. So they look at the different variation of the ViT, base, large, and so on, different number of layers and different dimension, and heads and parameters and so on. And these are their results. So if they train on JFD, because that's very important, they get pretty good results. But if they train on, the ImageNet, smaller data set, the performance not that high. It's comparing with ResNet and so on. So now, as we talk about transformer, you can come up with an attention map, and this is an attention map for these. So as you see that the network is learning to pay attention to those important areas where this particular object is, and it's a high attention as compared to the background, which is good. Okay, so that's what we have. I don't know why I repeated that. Okay, yeah, so now we will take the CLS token, MLP head, and do the classification. Now, classification loss is, as you guys have used before. So I just wanted, the slide is from the same presentation. Just want to repeat again to make sure you understand the concepts. So you guys know from physics undergraduate class, something called entropy. So entropy is defined like this: probability multiplied by log probability. It's a disorder, it's how many number of bits you need to represent something. So then now main important concepts in deep learning is that when we train a network, say to classify images in the ImageNet, it will predict a 1000 dimensional vector. And that is basically a distribution. Will tell you that what's the probability that class 1 is present or class 2 is present. So it's a distribution. And then you have a distribution from ground truths. It's basically hard, one hard coded. That if it's a frog, it'll be only one at frog and the rest will be 0. So the loss function traditionally is derived from this concept, what is called KL divergence. If you have two probability distribution, P and Q, you can find the distance between them by using KL divergence. These were the two researchers. And it is defined as the probability of I for all possible values of I, and log of P of I divided by Q of I. So that's very important. So first is from P to Q. So this P should be in numerator, Q should be denominator. And we can write down like this because log, we can do denominator can be minus. So this is the KL divergence you will see again and again. So simple that we are dealing with the probability distribution and finding the distance between two probability distribution, for example, probability predicted by the network and probability distribution of the ground truth, we can apply the scale divergence. So now, from here, we can look at the notion of what is called cross entropy. So when we look at this, Pi, log of Pi first term, then Pi minus log of Qi. Now, in this first term doesn't tell us anything about the ground truth, and it just tells you about what's the network is predicting. So therefore, in the neural network, we use cross entropy. It was only the last term here. So this is captured our thing, and this is our loss function. That's why you always use cross entropy. But it comes from the KL divergence. Okay, and since it is also entropy, but here entropy is same distribution, P and log of P. Yeah, we have two distribution, P and Q. So that's why it's called cross entropy. Now, as you see, this is not symmetric. So here is P of I log of Pi minus P of I minus log of multiplied by log of Qi. So if you do KL divergence between Q and P, it will be different. So it's not symmetric. So there is a symmetric, distance between two distributions. It's called Jensen-Shannon divergence, and which is essentially we find the M, which is half of sum of P and Q, and we find the distance between P and M and Q and M, and we add it up. And it's called Jensen-Shannon divergence, and this you will also encounter. So just keep in mind. Okay, so now other breakthrough came after the ViT called Swin. So Swin was published in 2021 in the ICCV conference, and it got a MOR prize, which is the most prestigious prize you can get, or the best paper award in computer vision. And Swin Transformer actually improved on the top of ViT. So let me cover that quickly and then we'll end. So as you by now realize, the adapting transformer from language to vision is challenging, and difference between language and vision domain is, first, there's a large variation of scale in visual entities. So, you can have a dog at different scales, right, different distance, but it still is a dog. But if you look at a dog word in NLP is a dog, D-O-G, it's the same thing. Other is that, an image has a lot of information, right, as compared to words. Because, if you want to store a video or image compared to some document, you need a lot of memory. So that's a problem. So that was one of the reasons that, transform was delayed in the vision compared to NLP. So main computation is self-attention, as you saw, that we are taking each token, finding its attention from all other tokens. And there are so many tokens, then we are doing so many computation, that's a problem. So this Swin, they came up with a very interesting idea to do this attention in hierarchical manner and do attention not in the globally for the whole image, but in a window, which is smaller than the whole image. And they use a shifted window, and that's called Swin. And it limits attention. So we are doing the local windows, and we want to allow the cross-window connections, okay? So, and they got much better results than ViT, and it's faster. So it's, this one accuracy on ImageNet, and not only ImageNet, classification, but they did other tasks, dense prediction, like object detection, semantic segmentation, and it surpasses the other approaches, which was good, COCO and EDI 20K and so on. So now we are going to look at the hierarchical feature maps and local attention. So as we explain ViT, we are looking at the 16 by 16 page, and it remains same throughout the layers. And so this token will get attention from all other tokens. So there's a lot of computation. Now what they did in Swin, that their token is smaller, 4 by 4 in this level. And then they look at this window. So only attention of this token will be from these tokens. The remaining, we won't take their attention. So it's much less computation as compared to here looking at the whole image. So that is the Swin. And so this is the first level where we have 4 by 4. And then we will take the 8 by 8. We'll merge these pages and we'll get a bigger page, 8 by 8. And then again, attention will be for this one only in this window. Then we'll go merge again, we'll have 16 by 16. So this hierarchical way they are doing that, and also it is the window based, not the global attention. Okay, so this is architecture. So we start with an image, head, height, and width, 3 channels. So we'll have page partition, and since our page is 4 by 4, so we'll have these many pages in the whole image, and then it's 4 by 4, so 4 times 4 is 16 RGB, so 48. So each token will have 48 dimensional embedding. Then we will have these different stages of the Swin. So stage 1, so we'll do the linear embedding, and we'll have Swin Transformer block, and 2 of those. So then we will again get the same number of the pages, but we will increase the dimension to see, and I'm going to talk about that. What's the dimension? They did experiment with 96, 128, 192. We'll see the results. So then we'll have stage 2. Again, we'll do the merge, and then 2 blocks of Swin. I'm going to explain. Now we will have the 8 by 8. And we'll increase the dimension because from here C we could 8 by 8 is twice as much. So we'll have stage 3, same thing. Now we'll have 6 blocks of that page merging. So here now it'll be 16 by 16, and we'll increase to 4C. And stage 4, again page merging, be 32 by 32, and we'll increase this 8C. So these are the 2 successive blocks. So we start with input, linear embedding, multiple self-attention in the window, not the global, and skip connection, linear MLP. This is the same thing, standard transformer. Now, here is a difference that we will do here what's called sliding window. So we'll get this one, and then linear, sliding window, self-attention, skip connection, linear, and MLP. So let's look at a little bit more detail. So layer 1, we will have this kind of thing. This window, and each one has this. So now layer 1 plus 1, we are shifted, as you see, that we are putting this thing somewhere here, and this become like that. So, and that's important. It's making a difference because now you are getting, in a way, second layer, you're getting attention from more than 4 by 4. You're getting other half of the window also, so which is interesting. So so we have page is the small page here, and the window is a big one, and that's the way it works. Okay, so these are the 2 transformer blocks. So as I said, we take the previous embedding, Z, linear embedding, window, self-attention, at ZL-1, skip connection. Then that goes to here, linear embedding, MLP, and we add to the skip connection. So that's this thing here. And this is now the shifted window. So we'll take the ZL and linear embedding, which is shown here, shifted windows, multiple self-attention, skip connection here, and then take this one, then linear and MLP, and then skip connection 0 plus 1. So that's the way. So we have these 2 successive Swin transformer blocks. Okay, so they try these different versions, Swin tiny, Swin small, and all this thing. C is 96, and then 128, and so on, and different numbers of these layers, 22262 and 18, and so on. So they got good results, which are shown here, and these are the different parameters and all those things. Some more detail. This is ImageNet 22K pre-trained models, and then this is on the mask, the object detection. So they get pretty good result, as you see. 46 to 50 and 48 to 51. And this is on the semantic segmentation. Okay, in summary, we talk about ViT is a first vision transformer, but was trained on the huge data set of 300 million. And Swin implies the window attention in addition from where on other tasks, and give you state-of-art results. So that's the end.